Good morning, everyone. The last lecture we have studied, if you see the last two lectures, we have studied the type of crystalline solids. Then we have characterized how you have to define the unit cell in the crystal. The repeating unit cell, it will form the complete crystalline structures that we have seen. So today lecture, what we are going to see means we are going to see about the crystal systems, the type of crystal system. If you look at the solids in our earth, how many solids are occurs? If you look at the elemental solids, how you can categorize means you can categorize using the this kind of crystal system. How many types are exist? That is the thing we are going to see today lectures. Crystal system in general we can call this is crystalline families or lattice system, because why here we are calling crystalline family means any crystal you can categorize within this crystal system. That's why we are calling all the type of crystal system or families. Maybe one like in our family we are saying for our brother and then sister, then mom and dad, like that you can say. Then the crystal system also you can categorize like family, simple cubic, body center cubic, piece center cubic. These are the like kind of cubical family system, like that you can say. Anyway, we are going to see what is a simple cubic, what is a body center. Those things we are going to look at in the Bravi slide is. Right now we are going to study the simplest crystal system. Before studying the crystal system, how you can define that system? We need at least something. We need some parameter to define. At least we need some angles to define. Those things we are calling it's a lattice parameter. So this lattice parameter involving how you are going to define the given crystal system, because we are actually living in the three-dimensional space, so we are going to construct the crystal system in the three-dimensional space. In 3D space, if you want to mention one single point, at least we need three coordinate axes. Like that, if you want to define the single unit cell in the crystal system, again we are going to take the three orthogonal axes, the x, y, z, they are perpendicular to each other. We are going to look at that axis length in the unit cell. That is the thing we can define one parameter. Then there are three more angle. That is the thing we are going to look at in this picture. Here we have taken the cubical structure. Maybe it's a like rectangular kind of structure we have taken. Look at this diagram. If you look at this diagram, there are three axes. This is the x-axis, y-axis, z-axis. We have chosen the one of the corner as the origin of the coordinate system. If you look at that, how you can define this unit cell means you can measure the length along the x direction. That means x intercepts of this unit cell, that will be equal to a. You can call in general it is a. That is the one parameter. That is the intercept parameter. If you look at along the y direction, the intercepts of this here it is intersect. The unit cell is intersecting y axis at exactly this point. So that length we are calling it is b. Here it is shown here, the length along the y direction b. Like that you can define the z direction, the intercepts. Here you can take this length as intercept from the origin. That length here, if you look at this length, it will be equivalent to c. So hence there are three parameter. One is the intercepts along the x-axis, intercepts along the y-axis b, intercepts along the x-axis, z-axis c. These are the three intercepts to define the length of the unit cell. So the first three parameter is a comma b comma c. Now you can ask one question, another question. What about the angle between the two axes? Look at the x as well as the y axis. The angle here we have taken, it is given, it is gamma. So the angle between the x and y, it is gamma. The angle between the z and y, it is alpha. It is given in the diagram, it is alpha. The angle between the z and x, it is beta. It may be 90 or may not be 90. We don't know exactly which crystal because it depends on the crystal. If you are taking the cubical or rectangular system, the alpha, beta, gamma, these three angle goes to 90 degree. So like that, if you are taking any crystal system, at least we need minimum these three angles to define the orientation of the axis in the crystal unit cell. So these angles in general we can call it interfacial angles. So we need alpha, the angle between the x here in this diagram, y and z, the beta, the angle between the x and z, as well as the gamma, the angle between the x and y. These three interfacial angle we need to define the unit cell. Three intercepts A comma B comma C, then three interfacial angle alpha comma beta comma C. So totally 6 parameter we need to define the crystal system. Without the 6 parameter we can't define. So even you can take more variables, but it doesn't matter. This minimum 6 variable enough to determine the given crystal system. So based on this 6 parameter, how many type of crystal system exist in the world? One can ask. So that is the thing we are going to look at now. So, if you are asking how many type of crystal system is exist, means there are 7 types of crystal system is exist. What are those types? The first one, the cubical system, we are going to look at. The second one, the tetragonal system. The third one, orthorhombic system. The fourth one, it is monoclinic system. The fifth one, it's triclinic system. The sixth one, it is a robohedral. The other name for the robohedral is trigonal. Anyway, I didn't mention it here. When we are look at in the structure, I will represent the robohedral, or it's a trigonal system. The last one, it's a hexagonal system. If you are counting the number of crystal system, here it is 7. So the first crystal system we are going to look at the cubical system. Here the cubical system I have given in the diagram. Look at the cubical system. Cube, already we know from the mathematics how we can define the cube, means all the sides are equal. Here if you look at the intercepts, here intersecting, the cube is intersecting x axis here, y axis here, z axis here. If you look at the three intercepts, that means here the intercepts along the x axis, maybe if you are taking this, this is the origin, this is a point, maybe you can call it a small x, this point is small y, the intersecting point, this point is small z. So ox, the ox is the intersect point, o small x, that is x intercepts, that is equal to a. So now if you are look at that y intercepts, o origin to the small y, that length is a intersecting length along the y direction, whereas the exactly the crystal is intersecting y axis at that point, that length also a. Base is a cubical system, all the sides are equal. So then if you look at that OZ, the intersecting that along the z direction, it is also a. Hence, the cubical system, the intersecting parameter you can define, the OX is equal to OY is equal to OZ. That means the intercepts are equal. The three intersecting parameters are equal. Now, well, we can ask what about the interfacial angle? If you look at that interfacial angle, x, y, maybe now you can define the angle between the x and y, you can define the alpha. Here if you look at it is 90 degree, because it's if you are exactly measuring, it will form the 90 degree. Similarly, x, y and z, that will also form 90 degree. Similarly, z and x, it will also 90 degree. So the three angles, the alpha is equal to beta, the interfacial angle, then the beta is equal to gamma. These three angles are 90 degree. Then three intercepts Ox, Oy, Yz, that will be equal to A. So if it is satisfying these 6 parameters, then we can call that type of crystal systems is a cubical crystal system. The example for the cubical crystal system, if you are asking, that iron, copper, sodium chloride, NaCl, calcium fluoride, this will form the cubical crystal system. If you are taking the iron based material, if you look at the inside, it will form the cubical crystal system. Even copper, we are having the copper wires. If you cut it and then if you are probing inside the atomic level, then you can see that cubical system. Even sodium chloride, calcium fluoride. So these are the best example for the cubical crystal system. And we are going to look at that one, that is a tetragonal crystal system. Here look at that picture. This picture shows that the tetragonal crystal system. Now we can define the three intercepts, that interfacial angle. Look at that, if you are taking the origin is here, then the intercepts along the x-axis is small x, the y-axis OY is small y, here in the z-axis small z. So there are three intercepts. If you look at this diagram, the OX x intercept, if you are taking the length here, it is given, it is A. Then if you look at that y intercepts, that will be OX it's A. Then if you look at the y-intercepts, the length is OY, that will be equal to B. If you look at the Z-intercept, that will be equal to OZ, that is equal to, here actually it is given wrong way, that this OZ also A. So this is a tetragonal system. So here if you look at this intercept, actually in the tetragonal system, two sides are equal, one side is not equal, that is a tetragonal crystal system. That's why I am making the O is at this length is A, OX, this length also A, but that OY it is not equal to A, that is different length, that is B. Hence that from this intercepts point of view, OX is equal to OZ, these two lengths are equal to A. Then if you look at that OY, the third intercept length, that will be equal to B. In general, how you can define this crystal system in the point of intercept view, OX is equal to OZ, he is not equal to, these two are equal, it's not equal to OY. So this is the first intercept point of view, you can define the crystal system. But if you look at the interfacial angle, the angle between the X and Y, it is 90 degree. Again, it will be right angle to each other. Then ZY, that is again 90 degree. ZX, that will also 90 degree. Hence, you can define the three interfacial angle, alpha equal to beta equal to gamma. These three angles are equal. The angles are equal to 90 degree. Hence, the 6 parameter, the three intercepts should have obeyed this condition. Three interfacial angles should obey this condition. If this 6 parameter is matching with any crystal system, you can call that crystal system is tetragonal system. What are the example for the tetragonal system? The example, the white tin, indium. These are the two examples for the tetragonal crystal system. We are going to look at the orthorhombic system. This is a diagram for the orthorhombic system. I am going to make the intercepts in the x-axis is OX, that is a small x intersect. The origin is O. That along the y-axis, small y, that length OY is B. Then O is at here intersect, it's a small z. OZ length is C. So here three lengths are different, three intercepts are different. Hence, the OX here, the intercepts along the x direction is A, the intercepts along the y direction is B, the intersect along the z direction is OZ, that is equal to C. Hence, you can conclude the intercepts point of view, OX not equal to OY not equal to OZ. That means three intercepts are not equal in the orthorhombic crystal system. What about the interfacial angle? Look at that angle. If you look at the angle between X and Y, 90 degree, the alpha is equal to 90 degree. If you look at that Y and Z, beta, you can call anything alpha and beta, doesn't matter. Beta equal to 90 degree. Z and X, that angle I am defining gamma, it's also 90 degree. Hence, the three interfacial angle alpha is equal to beta is equal to gamma. These three interfacial angles are equal, that is equal to 90 degree. So, these are the six parameters for the orthorhombic crystal system. If any crystal system, just if it is obeying this condition, six parameter condition, then we can call those crystal systems are orthorhombic crystal system. Now we are going to see the next crystal system. It is a monoclinic system. I will tell why the name is monoclinic. First we can look at the picture, how it will be looking like that. So the monoclinic crystal system, it will be looking like this. That OX, first we can define the intercepts along the x-axis. If I am taking the origin is here O, the length along the x-axis OX, that will be equal to A. The length along the y-axis, the intercept along the y-axis, that is OY, that will be equal to B. The intercepts along the z-axis, that will be small z. You can call that length is OZ is equal to C. First we can write these three intercepts. So the OX equal to A, the OY is equal to B, then OZ is equal to C. The length are different, so the intercepts are not equal. For the monoclinic system, the OX is not equal to OY is not equal to OZ. So these are the three lattice parameter. It is defined the monoclinic system. These three parameter we can call three intercepts on the three axis. Here the axis it's not a orthogonal axis because of the one of the interfacial angles is not equal. Look at this picture. If you look at the three interfacial angle, this is a, maybe you can define this is the first condition. Maybe it's not equal. Now, what about the interfacial angle if you are asking? Look at that angle between the Z and X. It is defined as beta. So here we can use the different. The beta is equal to 90 degree. The angle between the X and Z. Then Y and Z, if you look at, that is alpha, that angle also 90 degree. If you are measuring, it will be right angle triangle. So you can define the alpha angle, the beta, the next interfacial angle, they are equal to 90 degree. But if you are asking the third angle, gamma, the X and Z, that here it's defined as gamma, the gamma is not equal to 90. It's less than 90 if you look at that, because it is like acute angle. It's not obtuse angle. The angle between X and Z. The third interfacial angle, it is not equal to 90. So you can define this kind of crystal system is monoclinic. It has to satisfy this six parameter condition. Three length are not equal, but two angles are equal. One angle is not equal to 90 degree. So the two angles equal to 90 degree. That's why we are calling it's a mono means one single. It's here single angle, that is one of the interfacial angle is not equal to 90 degree. That's why we are calling it's a monoclinic. So this is a monoclinic crystal system. So the example for the monoclinic crystal system, if you are asking, the sodium sulfide, ferrous sulfate, these two are good example for the monoclinic system. So the next crystal system we are going to look at, it is a triclinic system. So look at this picture. This picture shows it's a triclinic picture, a triclinic crystal system. So we have to define the three intercepts, three interfacial angle in this triclinic system. Here I am going to define the, again we are going to use the same thing. Origin we are taking is here. The x intercepts, that is OX here, that length is A. The y intercepts, here it is OY. My line is not proper, but you can draw. Its a length is B. The Z length, that means Z axis intercept of this picture, that will be OZ, that is equal to Z. So you can define the first three intercepts. The OX is equal to A, then the OY is equal to B, then the OZ is equal to C. So from these three intercepts, if you look at the length, these three lengths are not equal. So what you can do, the OX not equal to OY not equal to OZ. Oh, if these three lengths are not equal for the monoclinic system, for the orthorhombic system. Now, what we are going to see, we are going to look at that interfacial angle to define the triclinic is a different one from the monoclinic orthorhombic. How you can define means, here look at that alpha, gamma, beta. The alpha here it is representing, it's an angle between the y and z, that is alpha. That angle, it is again it's not that obtuse angle, it's an acute angle. So it is less than 90 degree. Next, if you look at the beta, the angle between z and x, that is beta, that is equal to b, it's also less than 90. If you look at the y and x, that is angle is gamma, that gamma is less than 90. Maybe instead of, if you are saying, anyway we are look at this diagram, some angle is looking like obtuse, some angle looking like acute. So what we can say in general, it's not equal to 90. So not equal to 90. This is also not equal to 90. This are also not equal to 90. Maybe some angle, maybe obtuse angle. So we can't exactly tell. So what we can say, these three angles are not equal. They are not equal. So you can define, maybe some of them are acute, some of them are obtuse, some of them are maybe not equal to 90, but some angle. So you can define the three angle. How you can define? So alpha is not equal to, it may be, if it is obtuse, beta it may be acute, gamma, these three angle are not equal, they are not equal. So once if this crystal, given crystal system, if it is satisfying this condition, three interfacial angle are not equal, then three lattice parameters also, they're not intercepts. Here we are not defining the lattice parameter, we are defining its intercepts. If these three intercepts are not equal, if the given crystal system satisfying these two conditions, then that crystal system we can call it's a triclinic crystal system. We are going to look at the crystal system. It's a robohedral. The another name for the robohedral crystal system is the orthogonal. The crystal system, it will be looking like that. First we need to define the three intercepts, then three interfacial angle. Here, if you look at the three intercepts, the first the intercept length, it's a OX, that will be equal to A. Along the y direction, the length will be A, the intercept is Y, the length is OY. Along the Z axis, the intercept is Z, the length is OZ, that will be equal to A. Hence, you can define the OX equal to A, OY equal to A, OZ is equal to A. So, you can tell the three axial length OX, OY equal to OZ, they are equal to A. So, this is the first condition it has to satisfy. Even cubical system also it is having the same condition. What about the angle? In the cubical system, the three angles are equal to 90 degree, that three interfacial angle. Here, the interfacial angle, the alpha, beta, gamma, they are not equal, but they are, sorry, they are equal, but they are not equal to 90 degree. This condition it has to satisfy. But here picture we can't really show because some angle looking acute, some angle looking obtuse, but that is not case for robohedral. The robohedral system if you are taking, if you are look at this one, the three angle if you are measuring alpha equal to beta equal to gamma, three angles has to satisfy this condition, but they are not equal to 90 degree. They are acute angle, they are less than 90 degree. The actually in solid manner you can say alpha equal to beta equal to gamma, they are equal. All the angle if you are measuring they will be equal, but they are not equal to 90 degree, they will be less than 90 degree. This is a condition it has to satisfy. Hence the sixth lattice parameter for the robohedral, the three axial length yx oy oz equal to equal, they are equal to some lattice parameter A. Three angles are also equal, one of them to they are equal each other, but they are not equal to 90 degree, they are less than 90 degree. If they are equal to 90 degree, then that is belongs to cubical system. If they are not equal to 90 degree, less than 90, we can call it a orthogonal crystal system or robohedral crystal system. Actually here robohedral or trigonal, it's not orthogonal, sorry. It's actually he had made a small mistake. You can just write it's a trigonal crystal system, robohedral or trigonal. Maybe wherever I'm telling that orthogonal, just you can change it. Orthogonal means all the three axes are equal to 90. You can generally you can define that is orthogonal. Here is a trigonal crystal system. So the example for the trigonal or robohedral crystal system, if you look at that, calcite is the best example for that trigonal crystal system. We are going to look at the last crystal system, that is a hexagonal crystal system. The picture is looking like that. Here we need to find the three intercepts, but how we are going to define the axis means first we have to choose the origin. What I am going to do, I am going to choose the origin here. Best we can choose the red, take the red. So origin is here, this point. The x-axis I am going to choose along this direction. This is a x-axis direction. Then y-axis you can maybe you can choose this axis is y-axis. Then z-axis you can choose this is the z-axis. Anyway, we can't do more than the three axes in the three-dimensional crystal system. The length along the z direction, it is a. Intercepts, you can call it a small z. Here, if you are calling the capital Z, capital X, capital Y. The intercepts along the y direction, this is a y length. That the length is c. Here, intercepts is small y. Intercepts along the x direction, if you are taking these intercepts, it's a small x. So that length is ox, that is also equal to a. So here the intercepts length ox along the x direction, that will be equal to a. Look at the diagram. Here actually it is not equal to b, it is that length also a. In the hexagonal system, the base length are all the length are equal. There are six bond will be there. If you look at this diagram, there are six bond in the top face, bottom base. Each of them have six bond length. They are equal in the hexagon system. That's why we are calling OX equal to A. Then OZ also here it is in the base length. Along the Z axis, that will be length also equal to A. What about in the Y direction? The OY, that length is equal to B. So in the hexagonal crystal system, the three intersect length, the OEX is equal to OZ, that will be, they are equal to A. The OY, that is different length, is equal to B. Hence you can conclude OX is equal to OY is not equal to OZ. OZ is different from the OX, OY. They are equal. Sorry, here actually OX is equal to OZ. not equal to OY. This is an important conclusion because here OY we have taken the length is C. Here it's not, actually it is B. Here small correction you got to make. The OY length is C. So OX, OZ equal to A, OY equal to C. So hence the final conclusion you can make. Suppose I want to erase this one without okay, properly we have to write here. We have to write OX equal to OZ, they are equal to A, not equal to OY. So this is the first condition it has to satisfy. These are the first lattice parameter condition, the three intersecting length. Now what about the interfacial angle? Look at that angle. The angle between the X and Y, it is 90 degree. Y and Z, that is also 90 degree. What about X and Y? The X X and Y, if you look at that one, it is equal to 180 degree. So you can call one of the angle the alpha equal to 90 degree. If you are taken the angle between the like Y and Z, the beta, if you are taking the angle between the X and Y, that will be 1 X and Y, not X and Z, it is 120 degree. Then if you are taking the gamma, the angle between the X and Y, that will be equal to 90 degree. Hence, there is another condition it has to satisfy. The interfacial angle alpha is equal to gamma, is they are equal to 90 degree. So the beta equal to 120 degree. That means two of the angles are equal, not equal to one of the angle. If any crystal system, if it is satisfying this two condition, that means 6 lattice parameter, we can call that crystal system is the hexagon crystal system. We finally we have given here the 7 crystal system together with the example. Look at the cubic system. The 3 axial length are equal, 3 interfacial angle are equal, that will be equal to 90 degree. That is a cubical system. Example it is given here. The tetragonal, 2 length are equal, already we have seen in picture. Then not equal to O, the another axial length. 3 angles are equal to 90 degree. Example ordinary weight in indium. The orthorhombic, 3 angles are not equal, sorry, 3 axial length are not equal, but 3 angles are equal to 90 degree. Example sulfur and topaz. Monoclinic means 3 length are not equal, but 2 angles are equal to 90 degree. One of them are not equal to 90 degree. The best example it is given here. That is sodium sulfate and then ferrous sulfate. The triclinic system, 3 angles are not equal, 3 axial length are not equal, then 3 interfacial angles are not equal. The best example copper sulfate, then potassium dichromate. So these are the triclinic system. Tri means 3 of them, tri not 3. Clinic means not equal. So triclinic. 3 angles are not equal, 3 length are not equal. You can call the triclinic system. Just you can remember in simple manner. The Robohendral, 3 length are equal, then 3 interfacial angle are not equal to 90 degree. They are equal but not equal to 90 degree. That we can call it's a calcite crystal. Then the hexagonal crystal system, the 2 length are equal but not equal to the third one, as well as the 2 interfacial angles are equal to 90 degree. One of them are not equal to 90 degree. The gamma, maybe you can use any symbol, it doesn't matter. The one angle is equal to 120 degree. Example, it's a quartz and then tourmaline. So this is our end of the lectures. Thank you.